Hey students, welcome to lecture 4 of heat and mass transfer. So by just what I said now, you should recognize that we'll be moving on to mass transfer in this lecture. Okay, we still have some important concepts to be covered in heat transfer. So we'll look at that before we jump on to mass transfer in today's lecture. Okay. First, we will look at a concept called as dimensional analysis. This tells us how many dimensionless groups are involved in a case we are studying or a phenomena that is happening, all right? In particular, we are talking about heat transport or mass transport or momentum transport phenomena, all right? So within which how many dimensionless groups are involved, we'll get to know that with dimensional analysis. Okay, and following that, in previous class we have looked at a simple form of heat exchanger called as double pipe heat exchanger. So heat transfer is not complete without knowing the other type of heat exchangers that are out there. Okay, so in an undergraduate class, you will spend some time designing these heat exchangers. However, since we are short on time, I will just give you a glimpse of the different heat exchangers you will find in industries. Right? So from there, we will move on to mass transfer. You will see how what you learned in heat transfer still applies to mass transfer, or how the equations are similar between heat transfer, mass transfer, and not only that, between momentum transfer as well, right? And from there, we will move on to diffusivity coefficient, or diffusion coefficient, or diffusivity actually, all right? And so we will look at how this diffusion coefficient is dependent on temperature and pressure for gases and liquids by looking at some of the empirical formulas that are out there, right? Okay, so the dimensional analysis is given by a method called as Buckingham method. Again, so with this method, we will estimate how many dimensionless groups are involved in a particular mass transport or momentum transport or heat transport situation. Okay, all right. So Buckingham theorem states that the functional relationship among q quantities or variables. So if you know of an example scenario, and we would be able to quantify how many variables are involved in that scenario, right? So if that q is known, and you can express those q in terms of fundamental units like mass, length, time, and temperature. All right, those are fundamental units, so you could express them. And with this formula of q minus u, you will know how many dimensionless groups are actually involved in that case. All right, so as an example, let's consider fluid flowing. Okay, let me get the laser pointer. Let's consider a fluid flowing in turbulent flow at velocity v. So v is one of the variable or quantities inside a pipe of diameter d. So d is another variable, and heat transfer is also happening through the wall. All right, so we want to know how many dimensionless groups are involved. Okay, so under this example, we know these are all the variables that are involved. Okay, so since heat transfer is happening, you have h, heat transfer coefficient. Since it's happening within a pipe, okay, diameter is also a variable. Okay, so fluid properties, density, viscosity, cp, thermal conductivity, and the velocity at which the fluid is flowing, those are all the variables that are involved. In total, we have 7 variables, and these can be expressed in terms of the fundamental units: mass, length, temperature, and time, right? So now q minus u, so we with Buckingham method, we estimate that there are three dimensionless groups involved. Okay, so basically, for this scenario, we can have a function in this form, okay, that relates these three dimensionless groups. Pi1 is a dimensionless group, pi2 is a dimensionless group, and pi3 is another. All right, and with this method, with dimensional analysis, we are going to find out what these groups would be for this example. Okay, and the variables that we have seen previously, they can be expressed in terms of their fundamental units as shown over here. Okay, so simple examples to illustrate what we mean here. So for example, diameter, right, it just has length as the fundamental unit. Okay, diameter, for example, has the unit of meters, so length. And the density, kilogram per meter cube. Kilogram is mass and meter cube length to the power cube. All right, so there are some errors as well. One, for example, is here velocity is meter per second, right? So therefore it should be L by small t. Okay, so this is an error. Okay, so this should be replaced by L. Okay, so likewise you can work out the fundamental units for the other variables. Okay, so you can, so you guys are all grad students. From there, from here you should be able to pick up and work it out. And dimensional analysis starts with the step. Okay, the next step is trying to express your dimensionless groups in terms of the different variables. So the way it is done is, since three groups are involved, we pick any three variables and distribute them across, and the remaining variables we keep it as a constant across these three groups. Okay, so it can be any three, all right, but the math that would be involved could be simple or complex depending upon which variables you pick to distribute. All right, so of course nobody knows it. Okay, so it's obtained only through a trial and error. One will get to know it only through trial and error. All right, so these are distributed, and now we want to know what is this A, B, C, and D. What are the values for A, B, C, and D? To find that out, so this is the math shown here. Okay, so the first functional, first dimensionless group is expressed in terms of these variables, right? We want to know what is A, B, C, D. Now you express this equation in terms of its fundamental units, basically. All right, so on this side, it's since it's a dimensionless group, it is unitless, so all the fundamental units have the power 0. All right, and on this side you express each of the variable in terms of its dimensionless we express each of the variables in terms of its fundamental units, basically. All right, now you equate. Okay, so here you have L to the power 0. Okay, so that should be equal to whatever power you have for L on the side. Okay, so 0 on your left hand side should be equal to A plus B plus minus C. Okay, so it's minus C basically. All right, and plus D, and you have L to the power 3 at the bottom, so it's minus 3. Okay, so likewise you can write down different equations for the four fundamental units you have here, and four unknowns you got. Okay, so A, B, C, D, so you have four unknowns, four equations, you can solve them. Okay, so you can solve them, so you get what is A, B, C, and D. All right, and substitute A, B, C, and D in pi 1. Now you get a very familiar form. Okay, so you get a familiar form that you can recognize, which is nothing but your Reynolds number, right? So you can recognize that pi 1 is nothing but your Reynolds number. So you repeat these steps for the other dimensionless groups, to be able to calculate now, first try it for the next dimensionless group pi 2 and calculate EFGH, and following that do it for pi 3, calculate IJKL. All right, and with that you will get these two other dimensionless group. Okay, so these are new dimensionless groups that you have not seen before previously. Okay, so one is Prandtl number, Cp mu by k is your Prandtl number. Okay, so and the next one is Nusselt number. All right, so Hd by k is Nusselt number. So this expression is, you should be familiar with this expression, right? So hd by k, in a previous class you saw an expression similar to this, which is hx by k, right? hx1 by k, but you should not mix both. Okay, so the one that we saw previously was Biot number. Okay, so it provides what is the conductivity resistance, the ratio of conductivity resistance to that of convective resistance. And to put it simply, the H you saw there was for the liquid and K was for the solid material. However, in this case of Nusselt number, you have H, of course, for the heat transfer coefficient within the liquid phase, and K is thermal conductivity for liquid. Unlike the solid, we had it with Biot number. Okay, so this kind of tells the relationship of heat transfer due to convection and heat transfer due to conduction that is happening within the same phase. Okay, so Nusselt number talks about that, compares convectivity to conductivity within the same phase. Okay, however, Biot number talks about when heat transfer happens from a solid material to a liquid material, so it compares whether conduction or convection dominates. Okay, so which one is providing resistance to heat transfer. That's what Biot number talks about. So don't mix them up, although the expression form looks similar. All right. Okay, so we will state the physical significance of these three dimensionless quantities later on in a different slide. That should also clarify, that should also provide further clarification for you. Okay, so basically for this scenario, okay, so your Nusselt number is related to the other two dimensionless group. Okay, so it's a function of other two dimensionless group. And so with this, we can conduct, or researchers have conducted experiments and developed semi-empirical forms that could be used to calculate heat transfer coefficient when all the other variables are known. Okay, so that is the other purpose of doing this dimensional analysis. Okay, so you get a start on how your mathematical model would look like. You conduct further experiments and do a regression analysis and develop semi-empirical methods, semi-empirical models with which you can calculate heat transfer coefficient in this case, for example. All right. Okay. And from your momentum transfer class, your Reynolds number compares inertial forces to viscous forces, right? And the Nusselt number, which we just saw, okay, hd by k. So since you have heat transfer coefficient at the top and you have k thermal conductivity at the bottom, so it kind of compares convection heat transfer to that of conduction heat transfer, which we just saw. Okay, and Prandtl number is Cp mu by k. So you rearrange it in this fashion. So it's basically mu by rho is nothing but your momentum diffusivity, and k by rho Cp. Okay, so which is your thermal diffusivity alpha, right? So your Prandtl number compares momentum diffusivity to thermal diffusivity. All right, so it compares momentum diffusivity to thermal diffusivity. Right. Okay, so said that the dimensional analysis is used to estimate the relationship between different groups, and this is the final form for the semi empirical formula for a heat transfer coefficient for laminar flow inside a pipe. Okay, so you could see that there is a relationship between Nusselt number, Reynolds number, and Prandtl number. Okay, so all the other constants, they were estimated by experiments, by doing experiments first and by doing regression analysis later on. Okay, so with that, so researchers were able to develop this model that is shown here for estimating heat transfer coefficient for laminar flow inside a pipe. Okay, so if you have a case where laminar flow is happening inside a pipe, you could use this formula and calculate your heat transfer coefficient. Okay, so the properties are listed over here, or at what temperature you will be estimating. All of these properties are listed over here. You can take a look at that. Okay, and again, okay, so from your momentum transfer, you should know that for a flow to be considered as laminar flow, Reynolds number should be less than 2100. So this equation applies only when it's laminar flow. Okay, so when you know that the situation is laminar flow, then you can use this semi-empirical form, and by substituting the other variables, or by knowing the other variables and calculating these dimensionless groups, you can calculate heat transfer coefficient basically. All right, and take a look at these description over here, so that at what temperature all of these properties are pulled out. Okay, so as you know, for example, viscosity depends on temperature, right? So you should know at what temperature you should be identifying the viscosity to be used in this equation. Okay, so read this carefully for that. Okay, and likewise, you have a different form if heat transfer is happening within, and heat transfer is happening within a pipe and the flow is turbulent. All right, so the flow is turbulent when your Reynolds number is greater than 6,000. Okay, so you guys know it from momentum transfer. Under that scenario, you can use this form to calculate your heat transfer coefficient. Okay, so again, read this description to know at what temperature these fluid properties should be evaluated at. All right, so these are to estimate heat transfer coefficient when flow is happening inside a pipe. And likewise, there are other semi-empirical forms to estimate heat transfer coefficient when a flow is happening around different geometries. For example, if a flow is happening around a pipe, or around a sphere, or around a plate, there are different formulas. There are different semi-empirical models which people have developed and can be utilized. You can refer to the textbook. Okay, so since we are short on time, I'm not going over those different models here. All right, so please take a look at that. Okay, so now we will shift gears to a different topic. So as I mentioned, okay, so one double pipe heat exchanger is the simpler heat exchanger, but in industries, okay, so when you'd want to if the area that is required is pretty large, right? So then your double pipe heat exchanger would be a pretty long. Okay, so it would be impractical to have a pretty long double pipe heat exchanger. Okay, so to compact it, so researchers have developed another type of heat exchanger, which is called the shell and tube heat exchanger. Okay, so it's called the shell and tube heat exchanger. Okay, how it would look like in an industry is shown by this schematic over here. All right, so a cross-sectional view is shown over here. Okay, So you either have the shell side, okay, so the fluid flows through the shell side, okay, so the fluid flows around the bunch of tubes over here, okay, so they flow in and it can get out, okay, or fluid can flow through these tubes. All right, so you can either have cold fluid flowing through these tubes and hot fluid, flowing through the shell side, okay. So that decision is based upon different factors, okay. So when you get into industries, you will get to know that, okay. So from practical experience, you will decide which one needs to flow through the tube versus the shell, okay. So for example, if a fluid is highly viscous, you don't want it to flow through the tube, right? Okay, so the pressure drop will be very high, okay, and in that case, preferably you have it flow through the shell side or something. For example, if it flows through the tube side, and if it can form okay, so if sedimentation can, however, if sedimentation can happen and it can plug the tubes quick, right? So such fluids, for example, okay, so preferably to through the shell side. So there are several practical decisions you have to make in deciding which fluid flows through the tube side versus the shell side, okay. And this particular heat exchanger is called as one shell pass and one tube pass heat exchanger, because the fluid flows through the tube side once and then it exits. All right, and likewise, the hot fluid in this case flows through the shell side once and it exits, okay. And so by I saying that it flows through once, okay, so if we are not clear with this, okay, so when we look at the next heat exchanger, one shell pass and two tube pass heat exchanger, it should be clear for you. All right, so the bottom figure is for one shell pass and two tube pass heat exchanger, okay. So basically on one side of the tube inlet you have divided that drum, okay. So you have, okay, so fluid can flow only through the tubes at the top, okay, so but it cannot flow through the tubes at the bottom, so therefore it exits on the other side and it flows through the tube once more. So you have two tube passes, all right, but on the shell side it flows just once, okay. And therefore this is called as one shell pass and two tube pass heat exchanger. So you do have multiple pass heat exchanger on the shell side as well. So for example, we have two shell pass and four tube pass heat exchangers as well. So you can Google for it, see how that schematic would look like, okay. So this is a shell and tube heat exchanger. So this is going to be the common type of heat exchanger you will see in industries. And in the undergraduate class, we will also have a lecture or two on designing shell and tube heat exchangers. In particular, uh, we will provide them approaches with which you can calculate the heat transfer area required for a shell and tube heat exchanger, but since we don't have enough time, we won't go over that, okay. Other type of heat exchangers are called as cross flow heat exchangers. So these are utilized when the heat transfer required is very small and you want to design some compact heat exchangers. All right, so you have one type of cross flow heat exchanger here called as one fluid mixed and the other fluid unmixed, okay. So the fluids that are flowing through the tubes are unmixed, whereas the fluid that is flowing around it are mixed, okay. So that's why it is called as one fluid mixed, the other fluid unmixed, okay. And you can also have other type of heat exchanger where both fluids are unmixed, okay. So the fluid flowing around the tubes are also not mixing in this case, okay. So that's called as a cross flow heat exchanger, but both fluids unmixed, okay. So these are used for compact designs usually. All right, this is one figure or image on how an actual shell and tube heat exchanger or the size of it looks like. Okay, so these are some of the common sizes you will see in industries for shell and tube heat exchanger. So as you can see, the tubes are thin tubes. Okay, so and often we will see that the tubes get plugged over time of usage, and that was one of those practical decisions you make on which fluid you would want to pass through the tube side versus the shell side, etc. All right. And I forgot to mention one important item in shell and tube heat exchanger. Okay, so these lines that you see here, those are called as baffles. Okay, so you see it as a cross section here, but you can see it in this 3D view over here. Okay, so that's a sheet. Okay, that's a metal sheet. Okay, so these are called as baffles. Okay, so it helps to hold the tubes together. Okay, so otherwise the tubes can bend. Okay, slag here, right? So it helps to it is for the mechanical design as well, mechanical design purpose as well. And not only that, it also allows the shell side fluid to flow through or take uh, take passes across the entire heat exchanger. All right, so if you don't have baffles, for example, okay, so in this case, okay, so you could imagine the fluid will take the shortest path to the exit, right? Then you will form a lot of dead zones. Okay, so to avoid those dead zones as well, you introduce these baffles. Okay, so they can also create turbulence within. Okay, so and you know that when you have turbulency, then your heat transfer coefficient will be high. Okay, so your heat transfer will be higher as well, and the design will be much more compact. Okay, so there are different purposes for having these baffles. Okay, and from here we will shift gear and move on to mass transfer. All right, so mass transfer occurs when a component, okay, so when a component in a mixture, okay, so if you have components A and B in a mixture, or if you have different chemicals within a mixture. So if you consider gas, for example, and if you have a helium and nitrogen in gas, okay, so that's what we are talking about. Okay, helium is one of those components. Okay, and a mixture migrates in the same phase. Okay, so helium migrating through the gas phase or from phase to phase. Okay, so migration could happen from a solid phase to a gaseous phase as well. For example, drying of wood, right? So then you have water molecules migrating from a solid phase to the gaseous phase. Okay, because of a difference in concentration between 2 points. Okay, so we saw in heat transfer that thermal energy transfers from high energy to low energy, which is basically given by temperature difference across 2 points. Okay, so when you have temperature gradient across 2 points, then heat transfer was happening. However, when you have concentration difference across 2 points, then you will see mass transfer happening. So what are the applications for learning mass transfer? So we have seen this important unit in our first lecture on heat transfer, the distillation column. And we saw that heat transfer is important in distillation, in the design of a distillation column, but mass transfer is also important. Okay, so it's because of mass transfer you are able to separate crude oil into these different fractions. Okay, we saw that vapors flow from bottom to the top and liquid flows from top to the bottom, and throughout the distillation column you will see that components get exchanged from one phase to the other, such that corresponding to the temperature in each of these stages, it will reach that equilibrium, and the fraction can be taken out as a product. Okay, so for that reason, okay, so mass transfer will be happening throughout the column. All right, and other examples, so you could design artificial kidneys. Okay, so kidney, okay, so mass transfer is happening for between one fluid to the other. Okay, so from blood to your urine, mass transfer is happening. Okay, so ions are being transferred. All right, and by knowing mass transfer, you can design artificial kidneys. Okay, some classic examples, and definitely you see mass transfer happening around as well. Okay, so when you lay liquid, okay, so in an open pail, okay, so water evaporates after a time. Okay, so you all know that water changes from liquid to gas phase when it starts to boil, right? But when you let water out there, when you let water sit outside, okay, so it's not actually boiling, but water disappears. Why is that? It happens because mass transfer is happening from the liquid phase to the gas phase. Okay, and a second example, you add a piece of sugar, okay, so it dissolves. Okay, so then you see mass transfer is happening. Okay, and with this I would want to point to two types of mass transfer we will study. Okay, so if you just add sugar and you let it sit for a while, of course the sugar will dissolve. Okay, and that is called as free diffusion. Okay, so that is called as free diffusion. But now you can take a spoon and start mixing it. Now you're actively engaging the sugar to dissolve it, and in this case it's called as a convective diffusion, free diffusion, or a convective diffusion, right? And when you let timber to dry, okay, so this is an example we saw previously. Okay, so mass transfer is happening. Okay, and in fermentation processes, okay, so nutrients and oxygen are diffusing to microorganism from the liquid phase. Okay, so you see mass transfer happening in catalytic reactions. Reactants are diffusing from the surrounding to the surface. Okay, and reaction happens. Okay, so diffusion, mass transfer is happening. Okay, and another example of SO2 removal from flue gas by a method called absorption. Okay, again from gas phase to liquid phase. Okay, so your mass transfer is happening. So different examples for mass transfer you see in industries as well as you see in day-to-day processes, right? So, Fick's law for molecular diffusion, it states that molecular transport can be defined as the transfer or movement of individual molecules through a fluid by means of random individual movement of molecules. Okay, so molecular diffusion happens because molecules are moving randomly. Okay, so molecules are moving randomly, and in this case you have A and B. Okay, so A diffusing through B, and if you have a concentration of A high at zero point 0.1, and as a result of these random motion, you would have a net flux of A from zero point 0.1 to zero point 0.2. All right, so that's molecular diffusion. Okay, more examples of your molecular diffusion here. So instead of an example we saw previously where we added the sugar into a fluid, in here we are adding a drop of dye into water, and as these dye molecules diffuse out, it's molecular diffusion, and you actively mix it. Now you have a convective mass transfer. All right, so Fick's law of molecular diffusion provides the relationship between mass transfer flux to that of the concentration gradient, which is expressed in terms of molar fraction. Okay, so if you have A diffusing through B, okay, so your mass transfer flux JA is directly proportional to the concentration gradient. Okay, so and to remove the proportionality symbol, we bring in a constant in here. Okay, so in the Fourier's law, you had a thermal conductivity, right? So likewise, you have diffusivity over here, all right? And negative sign indicates that flux is happening in the direction where concentration is decreasing, all right? So negative sign indicates that, okay? And you have the constant total concentration outside. Okay, so total concentration of A and B outside the derivative. So when you take it inside, then your CXA becomes CA, concentration of EA. So you can rewrite Fick's law in another form as well, all right? Okay, so again, to the new term you have learned here is diffusivity. Okay, so it provides so when you say DAB, it provides molecular diffusivity of EA in B species A in species B, right? Okay, and across 2 points, okay, so how would you estimate the molecular diffusion flux? So you would, like we did for the case of heat transfer via conduction across a flat plate, you will integrate this equation across 2 points. Across 2 points 1 and 2, where the concentration is known as CA1 and CA2, and you will end up with this expression. Okay, and for diffusion happening within gas, okay, so you can utilize ideal gas law and replace concentration with the form of PV is equal to nRT. All right, so you could N by V is your concentration, which is equal to P by RT. So by introducing what you know from ideal gas law, you can rewrite this expression in this form as well in terms of partial pressure as well. Okay, so you have different forms for mass transfer flux. Okay, so this is mass transfer flux when diffusion is happening, and when the diffusion is a free diffusion, okay, molecular free diffusion. All right, so this is not for convective diffusion. Okay, so we will learn the expression for convective diffusion later on when this is free diffusion or molecular diffusion. This is the form to estimate the mass transfer flux. All right. Okay, so when convective mass transfer is happening, analogous to what you saw in heat transfer, you have this mass transfer flux given by mass transfer coefficient. Okay, so like we had heat transfer coefficient H, now you introduce a new constant called as mass transfer coefficient. Okay, so with that you can estimate your mass transfer flux, right? Okay, and to be able to calculate your free diffusion flux, so you should know the diffusion coefficients. Okay, so there are tables people have estimated using experiments that you could utilize to pull out the diffusion coefficient. Okay, and as you can see here, diffusion coefficients have been provided for binary system. Okay, so in this case of air diffusing through ammonia. Okay, and diffusivity here, for example, for this case, it's actually 0.198 into 10 to the power minus 4 meter square per second, right? All right. So tables like these provide your diffusion coefficient. Okay, so in this case, it's for a binary system. So there is a separate formula when you would want to know the diffusivity when diffusion is happening in a multi-component system as well by knowing these binary diffusion coefficient values. Okay, so you can use that form to calculate when diffusion happens in a multi-component system. All right. The way what 10 power 4 is written here, don't confuse it. Okay, so it's the way it's followed in this book. So For this case, diffusivity for air through ammonia is basically 0.198, and when 10 to the power comes to the other side, it's basically 10 to the power minus 4. All right, so diffusivity for all this, for this column, okay, so for all of these values is in the order of 10 to the power minus 4. Okay, and just try to remember the order for diffusion coefficient of gases. It's 10 to the power negative 4 meter square per second. And when we look at diffusivity within liquid, we can compare this versus that. All right, so to see how diffusion happens in different fluids, all right, in gas phase versus liquid phase, because where it happens fast, where it happens slow. All right, from practical experience you should know that diffusion happens much fast in gas versus the liquid, right? So you can try to compare that by looking at the diffusivity value. All right. All right. So these expressions over here, so they can also allow you to calculate diffusivity, yeah, when the different constants that are associated with your components. For example, collision integral for components A and B. If that is known, you can use this expression to calculate DAB. Okay, so there is another form. Okay, so I think this is called as a Chapman-Enskog form, or there is another form given by Fuller et al., which utilizes atomic volumes. All right. So you can, there are expressions as well with which you can calculate DAB, semi-empirical formulas. Okay, so these are basically semi-empirical formulas. Okay, but the important takeaway from these formulas is this. Okay, so your diffusivity is directly proportional to temperature. However, it is inversely proportional to pressure. All right. So basically, yeah, when temperature increases, diffusivity increases. All right, so your molecular diffusion increases with increase in temperature. That's the concept you would want to know. Okay, however, when pressure increases, then diffusivity decreases. Okay, because diffusivity is inversely proportional to pressure, right? Okay, so that's the important takeaway from the slide. Okay, not the formula by itself. Okay, but there are example problems in the textbook with which you can practice solving or utilizing these formulas to go over diffusivity calculations. Okay, and if you know DAB, and if you know that it is a binary gas mixture but it's not multi-component mixture, and if you know DAB, so there is a derivation that says that DAB is equal to dBA, that is diffusivity of A in B. If you know that, then if you want to know diffusivity of B in A, they are both equal. All right, and that this applies only for binary gas mixture. Okay, so in the previous slide for the Fuller form you had atomic diffusion volumes. Okay, so there are tables from which you can pull out these atomic diffusion volumes. All right, and you can try to solve some problems on your own. Take a look at the book. All right, and this is a table that provides the diffusion coefficient or diffusivity for when molecular diffusion happens in liquid. Okay, so when ammonia, for example, diffuses through water, and diffusivity is provided, so for the unit of meter square per second, it's in the order of 10 to the power minus 9, right? So in the gases, it was 10 to the power minus 4. So this indicates that, from diffusivity as well, you can see that diffusion happens way fast in gases than liquid, right? That's what you would happen. Okay, so if there is a leak of any gas, right, if I'm not sure if you guys have smelled liquid petroleum gas. Okay, so if there is a leak, then you will get to smell the gas very immediately, right? However, for the case of a diffusion within liquid, okay, so it is pretty slow. You could have added, a sugar drop, or maybe a dye is a good example, right? So if you don't mix it, and if you want, just a molecular free diffusion to do the mass transfer, then it takes a while. Okay, so unlike how gaseous diffusion is faster. Okay, so it's pretty slow. All right, and with these diffusivity values, you can also see that as temperature increases, diffusivity increases. Okay, so what we saw for gas, that diffusivity is directly proportional to what temperature, but to be more specific, diffusivity is directly proportional to temperature to the power 3 by 2. And likewise for liquids as well, diffusivity is directly proportional to temperature. Okay, and that can be recognized from this form over here. Okay, so two different forms, so two different molecular forms, two different semi-empirical formulas from which you can estimate diffusivity, and you see that diffusivity is directly proportional to temperature, right? And there are examples in the textbook with which you can see how these formulas are applied to calculate diffusivity. Okay, so we'll end this lecture by looking at a new dimensionless group that provides the relationship between momentum diffusivity and mass diffusivity, so which is called as Schmidt number. Okay, so Schmidt number gives us the relationship between momentum diffusivity mu by rho versus mass diffusivity, which is diffusivity, capital D. All right, so Schmidt number provides this relationship. Okay, so for example, if we spoke about you mixing a liquid where there is a drop of dye, right? And we want to know which of these diffusivity is dominating, whether it is momentum or mass diffusivity, all right? Or if reaction is happening and things are being stirred, and you would want to compare momentum diffusivity versus mass diffusivity. For all these cases, Schmidt number is helpful. Okay, I will stop lecture 4 here, and I will see you all in lecture 5 and 6, which will be entirely on mass transfer. Okay.